Hello everyone, so I have decided to create these videos in which I explain a bit about stuff that has been going on in the lecture or in the homeworks, or maybe also explain some of the solutions of the homeworks. And I decided to do this in this video YouTube format for a number of reasons. First of all, I think that normally on a Tuesday afternoon after 2 or 3 hours of lecture, you're too tired to listen to anything, like to listen to me explain you something about the exercises. So that's not really useful. And secondly, I can here explain several topics that maybe are not interesting for everyone, but just for a small number of people. So if there's like a topic I'm talking about and you're not interested in it, you can just skip the video and go on, do something else. And the third reason is that sometimes some of the concepts are quite complex and it can be helpful to listen to them 2 or 3 times. So in this way, you can just go back and listen to the last minute again or something. So I think all in all, this is a quite useful method. I've never done this before, but let's see how it turns out. So the topic I'm going to start with is the stability analysis that you have already been doing in the course and in some of the exercises. The reason why I'm starting with that is because I think there's like still some unclarity for some people maybe. Maybe some of you already know what to do if you get an exercise like in the on the last sheet, but maybe you don't know why you're exactly doing each of the steps that you have to do. And I hope that we can clarify this a bit here. If you already know everything or you're just not interested, it's completely fine to skip this video. I think this is nothing that you is completely necessary for the exam. For the exam, you should go with the script and with the lectures that Martin provides. I think this is completely enough. If, however, you have some trouble understanding, I hope that this might help you. So, in stability analysis, we always regard a state that is in equilibrium. And we want to find out if this equilibrium is stable or unstable. So quite often the situation is as portrayed here. You have a equilibrium and you want to know if you slightly change the position or something, what will happen to this equilibrium. On the left hand side, by our intuition, we know that simply if we move the ball a bit to the left or a bit to the right, it will start to oscillate, and if there's some friction, it will come back to the point that it originally was at. On the right hand side, we also know that if we perturb the ball just a tiny bit, it will start to accelerate, and this is clearly a situation of instability. Physical systems are basically this. You have an equilibrium and you want to know what happens if you perturb them. They're just much more complicated that sometimes we cannot tell what happens by intuition, but we have to go through the math and find out what happens. So this is why we use the stability analysis in this mathematical sense. But never forget that the goal is always to, in the end, come back to this situation of equilibrium and say what happens if we perturb it a bit. Will it oscillate? Will it go unstable? Or will it go back to its stable equilibrium? So I hope it has become clear now why we want to do this analysis. And let us now focus for the next maybe 2 minutes or 3 minutes on how exactly we will perform this analysis in a really general case. Okay, so about the methods. The first and really important thing is to check which are the relevant equations. And these, in our cases, when you do like fluid dynamics, mostly the continuity equation, the momentum equation, the energy or an entropy equation or something. And for those, you also have to check what are the relevant terms that suit your problem. So if you talk about a sound speed, for example, it is quite important to have a pressure term in there. Otherwise, you will not get the correct result. If you talk about gravitational instability, there has to be some gravitational potential or something, or gravitational force on the right hand side of the momentum equation. If you're sure that you have the right equations and your background satisfies the equilibrium condition for these equations, then you can start to linearize these equations. As you already know by now, I think, is in this linearization process, if it is necessary, you can use the background solution. So you can use this condition that you have for the background for equilibrium, and then all the perturbations that are higher order than linear, they go to zero. We do this because it makes the equations much simpler and actually allows us in many cases to find an analytical solution, while if we have the quadratic and cubic terms in there, it is just sometimes impossible to find an analytical solution, and one has to do numerical studies in that case. So, but yeah, the analytical solution is very important, because also for the numerical things, sometimes we don't exactly understand what is happening. And in the analytical case, we can exactly see which term influences the perturbation in which way. Okay, once we have linearized the equations, we will put in the expressions for the perturbations. So at this point, I think it is quite useful to take another look at these expressions. I think that some of you might just take the exponential function, these wave functions that we plug in for the perturbations, without actually knowing or understanding why we use exactly these expressions. So let's start from a general perturbation that is like a perturbation in space x. In this case, x should be in general, it should be a three-dimensional vector, but for simplicity we will take a look at this problem in 1D. So here now x is simply a scalar. So if you perturb something, this has like some shape in space and in time. Let's say you knock against a table. It's like it has some certain extent in time and some certain position in space where you perturb this table. So we will make use of the fact that this function of x and t you can always express as its Fourier transform in omega k squared space. So in a frequency and a spatial frequency space. And as you can see in this function here, there's already this e to the I kx plus omega t that you're always using. But there's still this integral, so you integrate over all possible or all relevant combinations of omega and k that contribute to this function f of x and t. Now we do a simplification, and this is, instead of looking at this entire function, this integral over the entire real space, we just look at one singular mode. A mode is this. So one function of k and omega is one mode. And we analyze one mode, but we do this in a general way. So we don't plug in anything for k and omega at this point. We keep them as variables. And in the end, we can check how do these modes behave. If all modes are stable, the entire problem will be stable. If all modes are unstable, the entire problem will be unstable. In some problems, we have some stable modes and some unstable modes, and there will be a condition for stability. And we will talk about this probably later on. For now, you see that doing this, it is a simplification, but we don't lose anything of the meaning for later on. So instead of checking how the entire integral behaves, we check how one singular mode behaves, and we can generalize the result afterwards. So once you have inserted these expressions for the perturbations, it makes life a lot easier, because now you can rewrite the expressions for time and space derivatives by simple multiplications. And then the next step is to solve the system of equations. You can do this in any way that you like, but I think just the nicest and easiest way is to rewrite the equations in a way that it looks like this. You have I omega times the perturbation vector, which lists like perturbation of rho and velocity and whatever you perturbed before, and is equal to a matrix times this perturbation vector. And then to solve this system of equations, you don't have to think much. You just have to solve the determinant of this matrix minus I omega times the unity matrix. Set this to 0, and you get an expression for omega. This expression for omega is the key, because it then allows us to reinsert this expression for omega into the original perturbation equations and interpret the solutions. From this, we can say how the perturbation evolves with time. If there is a real part in the exponential function that is negative, this is just a damping to the original state. If there's a real part in the exponential that is positive in front of the time, this means there is an exponential growth, which means it is an instability, because exponential growth is unstable. And if there is no real part but just an imaginary part, then in the exponential, which means that omega itself is real, then there's just an oscillation without damping or without growth. Don't get confused, I changed the background a bit while you were listening to this, but I hope that in this first introduction you got a better understanding of the background of the stability analysis, why we're doing it, and how we're doing it, and where the methods come from. In the future, I will try to analyze a few well-known systems like the sound waves, maybe the gravity modes that you had on the exercise sheet, and something like Rayleigh-Taylor or Kelvin-Helmholtz instability, depending on the feedback that I get from you, how useful these videos are for your understanding of the things. Alright.